Can everyone hear me? So for my final project, I wanted to do something that I would actually use. So something like that was a need of mine on a personal day-to-day basis. And I created a duplicate file finder because I have multiple different hard drive clusters because I want to make sure my data is safe even if my house were to burn down. And over the years, I've been collecting lots and lots of files. So each cluster is probably 1 million files or more, and they take up around 8 terabytes each. Duplicate files are hard to find because over the years I have had different file naming conventions, and I've sprinkled files in all different directories. So the same file could be in 10 different places and have 5 different names. So what I care about more is that the content of the file is the same rather than the file name or where it is at. And I couldn't find a good duplicate file finder in Windows. Like CC Cleaner will find like 4 files. And I'm like, I know I have more duplicate files than that. So the solution I had was first I scan all the files in the directory. So I had to learn the OS library for that. And using that, you can take every file in a given file location. And I am getting the file name, the file path, the size, and the modified date. And just as an aside, I'm outputting this to a text file, which says all files, because I also found that there's no good way of getting every file output into a text file. And using this file, I can run analysis in Excel or like do analysis in pandas or stuff like that, if I wanted to do some analysis on all my files. The next thing I'm going to do is group the files by size in a dictionary, where the size will be the key. And I'm doing this because grouping by size is very fast, and this will give me a subset of files. So if there's only one value for a given size key, I know there's no duplicate file for that. So if there are 2 or more files that share the same size, I'm going to store them and put them in a list. And on that subset of files, I'm going to run a hash program. So I use the hashlib library to hash all the files that could be possible duplicates based on the size in bytes. And next, I group by the hash key. So I create a second dictionary which uses the hash as the key. And some of the files will only have some of the hash keys will only have one file associated with them, which means that even though the size was the same, they are different files. So what I'm left with at the end is all the lists in the, I'm left with all the files in the hash dictionary where the values were 2 or greater. So given that the hash key is the same, I'm fairly confident these are the same files. This is basically, this is how I spec'd it out because I was getting lost in all the values. So I actually had to write everything down, and I just went through textually all of this, but this is an indication of how I thought the program would run. Here is the structure of the flist, which is a list that contains all the files. And it contains the file name, the path with the file name attached to it, because later in the program I have to retrieve information on a given file. So I need the full path to retrieve that file again. The number of bytes that the file takes, and the epoch date, which is the Unix way of showing a date. So I also convert both the bytes and the epoch date into user-friendly outputs, so you don't have to understand these decimal spaces. Here is the structure of the hash duplicates, which are the final duplicates, which I output to a duplicate files text file. And here I should be able to, so here is a program in use. So if you notice, it's running on a directory with around 100,000 files. With exclusions, it's going through 75,000 files. And it takes around 12 seconds to run. You'll see that it found 70 4,000 files or so that take up about 100 gigs, and there are 2.5 gigs of possible duplicates. Okay, so here is the output of the all files text file, and it contains the path. It contains a summary up top, the path, the more user-friendly, user-readable size, and the user-readable date. This is what the duplicates found text file looks like, and it contains the duplicates found, and it will show you there are two files, each that are 230 MB, and the saving is basically if I were to only keep one of those files. So here, if I were to delete one of them, I would save 230 MB. The second group has 4 files, each of 76 MB. So my total saving is if I deleted 3 of those files. And there are probably a few thousand pairs in this text file. What I found interesting is how quick hashing is. So I thought it would take forever, but maybe it's a modern machine combined with an SSD, but that program hashed 20,000 files, and the whole program ran in 12 seconds. So the hashing must have been maybe 8 seconds at tops. The other problem I found, which was an error that took me a while to solve, is I guess I had some files that had modified dates prior to 1970.
Springtime for hip.
Yeah, it didn't like those files. So I had to, it was actually useful to find them because I know I don't have any files that old, that should be that old. So I basically changed their modified dates in the OS, and then it ran fine. But the program does have some problems with files that are older than 1970. The limitations, since I have to give it a file path, I can't just say scan my computer. So it will only scan one hard drive at a time. So if I want to scan multiple hard drives, like 4 different hard drives, I'd likely have to give it 4 inputs and then create a master little files directory and then give that into the program.
So you have files older than 1970?
Well, they had dates older than 1970. How they ended up with those dates, I have no clue. So I have no clue how maybe someone had maybe I had the wrong date on a computer. The BIOS had the wrong date, so when the file was created, it created it with an old date. But yeah, they weren't that old, but it said they were that old. I'm also hashing so I have 2 modes of hashing in this program. One that hashes only the first 64K of the file, and a second mode that hashes the whole file in 64K blocks. It took 12 seconds for the fast hash. It took 20 seconds for the slow hash, so not that big of a difference. So for my purposes, I'll be running it in slow, more accurate mode. Jeff did recommend hashing the last 64K of the file, which I tried to find the syntax for, but I couldn't find it. The other problem, as I mentioned earlier, is invalid inputs. So right now, the program doesn't catch and throw errors in a user-friendly manner. If you give it a date older than 1970, it's going to have a hard crash. And if you were to give a letter as a size, it's probably going to crash hard. So those are things I would probably improve in the future. But I've already used this, and I find it useful because it allows me to find files that, well, fix problems like files with dates older than 1970. It let me find files which, like my TurboTax was taking, had 2 .NET installation files. I don't need either of them, so I can actually save the whole size for those. But yeah, any questions?
It'll install it again this year.
How important was the size measurement in identifying duplicates?
So given how fast the hash works, maybe I could have skipped that entire portion and just hashed everything. But I figured that hashing would be very intensive. But 20 seconds to hash 20,000 files is like fast. So maybe I could have simplified this just by going straight to the hash dictionary. So I was using the size because I figured size would be very fast. Like I wouldn't have to hash it if the size was the same. Because if the size is different, I know the hash key is going to be different.
The same file can record different sizes on different file systems, different machines, depending
Well,
on where it's block listed.
well, I'd be running it on one machine, I hope. So yeah, but the hash is, so the size gives me possible duplicates.
Right.
The hash gives me actual duplicates. I was using the size to basically create a subset of files because I didn't want to hash everything. Given how fast hashing is on an SSD, I guess I could hash everything. But if I'm running a spinning disk, maybe this approach would be more useful. Yes?
What would be the benefit of hashing the last 64K of the file as opposed to the first 64K?
So,
I'm curious about that. I have an idea about it.
yeah. So for me, like I found like 4 BMP files in there. Those 4 BMP files were actually different, and the first 64K were the same. So for very large files, I guess the first 64K can be the same. And Jeff probably knows the answer to this
File
better.
format probably, right? To some extent.
It could, I'm surprised you'd have a 64K header. But typically, if you're editing some kind of text file or program file,
Changes in
you're
every
quite
view.
often working at the bottom than the top.
That's what I thought. Yep.
Yeah, for the BMPs, they probably have a lot of information in the beginning, and they were the same picture, but they actually had edits made to them. So a good chunk of the data might have been the same, and it was probably just applying the edits. And BMP files are like 76 MB, so the first 64K could have been the same, even though they were different files. So I actually did want to implement your approach of using the last 64, but the slow mode of hashing, where it hashes the whole file, is very accurate. Any other questions? Thank you so much.
Thank you.
Thank you.